I guess what we're talking about, let's also just make sure we understand that mass, the difference between mass and weight. Difference between mass and weight. We've talked about it before, but this will be the final time. And you've got to and so many times people just don't get it. They just don't get it. Mass, they just want to make them the same thing, but they're not. Because mass is the amount of stuff you have. What's weight? We've already defined that. Weight is the gravitational force on an object. It turns out that the gravitational force on an object near the Earth's surface is the mass of the object times the acceleration due to gravity, and in the downward direction. That's an object's weight near the Earth's surface. And notice that, therefore, that the weight, we can call this the weight, the magnitude of the weight, which is usually what we mean by weight. The gravitational force is mg down. The weight is, we usually mean that's just the magnitude of that, which is mg. The weight is proportional to mass. That's why people want to make them equivalent, right? The weight is proportional to mass, but it's not equal to mass. Weight and mass are not the same thing. Weight is the gravitational force on a body, mass is the amount of stuff that you have. Go to the moon, right? Let's take our baseball to the moon. If I take our baseball to the moon, does the mass change? No, the mass doesn't change. The number of atoms in the baseball doesn't change. The mass doesn't change. The inertial mass doesn't change either. But does the weight change? Yes, the weight changes because the acceleration due to gravity on the moon is different than the acceleration due to gravity on Earth. Weight is not mass. Your weight can change depending on the local acceleration due to gravity. This can change, but your mass does not change as long as you don't lose weight, right? As long as you don't go on a diet. Your mass doesn't change. The amount of stuff that you have is the same. Weight is not mass. They're two different things. They're actually two different quantities. So the fact that they're proportional on the surface of the Earth, they're also proportional on the surface of the moon, that just tells you something different. But they're two different quantities, right? Imagine that your car breaks down on the road. If your car breaks down on the road, let's say you're on Rivermont Avenue outside of the college and you just want to get it into a parking space on campus. How do you get the car to your parking space on campus if you don't want to call a tow truck? What do? You take off the parking brake, you put it into into neutral, and you push it, right? You push it because when you're pushing it, or let me stop that sentence. You push it as opposed to, what is something else you could do? Well, you could lift it up and carry it. But which one of those would you really do? Would you push the car or would you lift it up and carry it? When you're pushing the car, you're pushing against friction and mass. So there's two things, right? So let's get rid of friction. So when you're pushing the car, you still have to exert a force. Even if you could get rid of friction, you still have to exert a force because you've got to overcome the inertia. But you can do that. Every single one of us has probably at some point in our lives pushed a car. I don't know if that's true, but certainly most people have. And we can therefore overcome the inertia of the car. You know you can do that. You have the strength to do that, to overcome the inertia of the car, and you can push a car and make it move. But can you pick up a car and take it home? No. None of us can do that. None of us can pick up a car and take it home. Because in the first case, when you're pushing it, all you have to do is overcome the inertia, the mass. In the second case, when you're lifting it up, you've got to overcome the weight. Those are two completely different things. You can't overcome the weight because it's too big, but you can overcome the inertia. You can always do that. I have a demonstration of that.
So this following video, 1,000,000 to 1, is an old film reel that I took a video of, and that doesn't exist anymore. So this is the best we can do. It's not great quality, but interesting.
You fill that can with solid carbon dioxide. Now you know solid carbon dioxide is very cold. This white stuff is just frost that's gathered on the outside of the can. Dioxide evaporates and turns into a gas. The gas takes up more room than the solid, so it has to go somewhere. It can't come out the top, so it comes out a little hole here at the bottom of the disc. You can't see it coming out the hole, if I make a plane, I think you can see that there's gas coming out and blowing the plane. Now if we put the disc with its stream of gas coming out the bottom down on our tabletop, which is made of a very smooth piece of plate glass, we can wait a moment while the gas coming out builds up pressure underneath, which it has to do in order to escape. By now, the disc is floating on this film of escaping gas. That film is so thin that I'm sure you can't see it from out there. I can scarcely see a space between the disc and the glass myself. But if you'll come and look over my shoulder, I think I can show you that there is a space. By slipping underneath the disc, this piece of tinfoil, I took off the chewing gum wrapper. Now we'll slip the tinfoil between the disc and the plate glass top of the table, showing that there is indeed a space, a thin film of gas between the disc and the glass upon which it's resting. The purpose of this is simply to reduce the friction to a point where we won't have to worry about it or measure it in our experiment today. It's fun to play with this thing. Let me show you. I'll give it a little push, just a little one. There it goes, moving sedately. No sign of slowing up. Come on back. Same thing the other direction. It takes only a very tiny force to start it in motion. Let me show you that.
So what was the point? Think about it, but I'll tell you now. We had a flea that was able to pull 1,000,000 times its mass. I don't know if it was 1,000,000 times its mass. You could figure it out. It's a flea versus a textbook, and on top of a frictionless puck. And the point being that all the flea had to do was it had to overcome the inertia. It had to overcome the mass, not the weight. It didn't have to overcome the frictional force. We got rid of frictional forces. And so it just had to move the mass. And so it doesn't matter what force the flea exerts. It's not that fleas are particularly strong. It's just that it doesn't matter what the force the flea had to exert, as long as it doesn't have to overcome any forces, and all it has to do is overcome the inertia, that it can move any mass, right? It can move mountains. An astronaut in outer space can move a satellite Because there is no friction, they don't have any forces to work against. All they're doing is overcoming the mass. Okay, have a good day.